All right, so here's particle motion part 2. Yay, woohoo! All right, so the very first question, and we've talked about this one in class, but it's always good to review. You have a function in standard position moving along a horizontal line given below. Which of the accompanying graphs represents the velocity of the particle? Well, again, we have to remember our relationship between the original function and the first derivative, and we know that if we take the derivative of the position function, we get velocity. And also, if we notice something about this graph, then we see that this graph here is strictly decreasing. That's the only thing this does. So if my function, my position function, is strictly decreasing over all these time values, then I know that my velocity function is going to have to be less than 0 or negative. And what does that translate graphically? Well, graphically, that implies that the graph is below the x-axis everywhere. So if the graph is below the x-axis everywhere, then we need to go look and see, well, which function could that possibly look like? And that's going to be answer choice D. For this next problem, we are asked at what time does the particle reach its maximum speed? And so our relationship here, and notice we need to look at what this is the graph of, and it looks like this is the graph of the velocity function. So how would our velocity function and speed be related? And that's on the sheet that I gave y'all. We are told that if we take the absolute value of velocity, then we get speed. And so that means that we can turn our velocity function into a speed function, because if we're taking the absolute value, we're making all these parts that are negative positive. So I'm going to take this segment that's below the x-axis, and I'm actually going to flip it over to be up here. And so I'm going to connect those, hopefully try to, something that looks like this. And then it looks like we have this segment here. And then we have another segment that goes all the way up to 5, don't we? So over here, all the way down to 3 also. And then we come back down to here. So here's a rough drawing, and that is rough, of the speed function. So now if I look at this and ask you, well, when or at what time does the particle reach its maximum speed? Well, that's pretty easy to pinpoint now. It's right there at time t equals 5. So your answer choice is A. Okay, for the next one, and we're going to use this graph for all of these questions here all the way through 7. The very first one asks you, using the graph, how many times does our particle change directions over the time interval from 0 to 8? Well, let's see, how many times would we change directions? Well, we know a particle is at rest when velocity is equal to 0, so I might want to look and see, well, when's velocity at rest? Because the particle might be getting ready to change directions. And in this case, it does. Notice that my particle, the velocity here is positive. So if my velocity is positive, then the particle is traveling to the right. And then down here, velocity is negative. So that means that my particle is traveling to the left. And so how many times would my particle change directions? Well, it looks like it changes directions once at t equals 3. Okay. Looking at the next one, according to the graph shown, where is the particle slowing down? So we really could go back over and look at our graph and change our graph of velocity to be a speed function. And again, that would be just like what we did earlier. We would be taking all of these parts that are below the x-axis, and I would flip them over to above the x-axis. So instead of going all the way down to -4, this particle at 5 would be at +4, so it would be way up here somewhere. And then it would go to its constant value. So if that's the case, then again we see where we have really the interval of decreasing would be from 2 to 3. So that would be a nice quick way to figure out where my particle would be slowing down. Now, another way to do this, if you didn't want to go through all of that graph stuff and flip over the graph where you might get confused with that, then we could have looked at here where my speed would be slowing down when my graph is, the graph of the velocity is above the x-axis and decreasing. So again, we could look to see where the velocity, again, all of this is based on if I'm given the velocity function, we could look and say, well, above the x-axis and decreasing, that would mean speed is slowing down. Or we could say that we are below the x-axis and increasing. That would imply that we had different signs, and both of those graphically would imply that speed is slowing down. So either way you want to do this is up to you. And so again, you can make your graph of velocity into a speed function, or you can look for these two characteristics. Right, and then in question 5, according to the graph, how many times for the time between 0 and 8 is acceleration not defined? So we're looking to see where I might not be defined on my graph, and this would be on your pink sheet. And it's really, you're not going to be defined whenever you have those sharp points and cusps. So let's look. Where would we have some sharp points and cusp? And we would have at least one sharp point here. And it looks like we might have another sharp point here. And I think we forgot to see that in class, that we would have those two sharp points. I know we focused on this one, but I don't think we noticed that that one also has a sharp point down there. So it looks like, how many places would I not have a derivative existing? It looks like we would have 2 places that my derivative would not be existing. So number 5, I would say is B. Okay, for number 6, we have the same graph, and we want to find for this one average acceleration. So average acceleration, anytime you're seeing average here, I want you to think about that slope formula, because if we're looking for average acceleration, we're going to be finding really the slope using our velocity function. So that's where a lot of people, a lot of times they get confused trying to find a derivative, but you don't. Average acceleration over this time interval is going to be v at 5 minus v at 2 all over 5 minus 2. And then you go to your graph, and v at 5 is -4 minus, and then you see minus 2 all over 3, and you do your nice little number magic here, and it looks like you should end up with -2. Okay, and now let's see. Let's look at number 7. Number 7, at what time in the graph does the particle first reach its maximum speed? And I think by now we're pretty used to just looking at this, and we know all of this stuff that's flipped over being negative. We know really if we talk about speed, we have to imagine that flipped over being positive. So it looks like here at 5 is whenever our particle first reaches its maximum speed. All right, so for question 8, according to the graph shown, for what value of t is the particle's position farthest to the left? Now we have to remember that when we're talking about left and right, then we need to remember that we really need to consult the velocity function. And this is the graph of the velocity function, so that's great. We know that when velocity is negative, then the particle is moving left. And we know that when the velocity is positive, my particle is moving to the right. So really that translates graphically that we're really looking for either above or below the x-axis. And so let's see here. Let's go look and see, because we have a lot of places that we are below the x-axis. Notice here at A all the way, so we're still, think about this as we're traveling left, and think about the particle, it's a crackhead. Particle crackhead, we're traveling to the left, 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 left. He's still traveling left, 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 left. But at point C, this old crackhead sees a cop, and what happens here? Well, he sees a cop, and he's going to turn around, and he's going to start traveling back to the right. He's running away. So notice just this time period, our crackhead particle is traveling to the right, but down here, my goodness, he's traveling to the left this whole time. So if he's traveling to the left this whole time, where's the farthest point he would be to the left? I think it's safe to say that would be at point C. Okay, so now let's look at number 9. And again, this is another question about asking for maximum speed. So looking at our graph, and we can flip out over all those negative parts on our graph. And if we imagine everything that's below reflected over the x-axis, then I think it's safe to say that B should be the correct answer here. Okay, so now we need to look for where is the speed, or where's the particle speeding up, and where would it be speeding up at? Well, this is kind of the complete opposite of what we said earlier with the other. If speed is increasing, then we have the same sign for velocity, and acceleration would have to have the same sign. So what does that mean graphically? Because algebraically, okay, they're both positive, both negative, but what about a graph? Well, here if you want same sign, you've got two choices. One, you are above the x-axis if you have the graph of velocity and you are increasing, or your second option would be below the x-axis and decreasing. That would give you where your particle would be speeding up. So if we look at our graph where we're below and decreasing, and then above and increasing, so it looks like that might be answer choice E. Okay, number 11 wants to know, well, for what particle, or for what times t would my particle be decreasing? Well, it's right the opposite of what I just wrote, so we need to be acceleration and velocity have different signs. And where in the world are they going to have different signs? Well, that's going to be where we're above the x-axis and decreasing, or below the x-axis and increasing. Or we can flip our graph over and look at that graph. Either way, hopefully we get answer choice A for that one. Okay, the next question asking us, Here, which statement best describes, oh, these are always a joy, best describes the motion of the particle between B and C. So between B and C, let's see, let's just go through our answer choices and look back at our graph and see. So for A, the particle is moving to the left at a constant speed. So between B and C, our particle is moving to the left, but it's not a constant speed. My function is increasing there, so I don't think that would be a good choice. Okay, so let's look at B. The particle is moving left with a decreasing speed. Particle is moving left with a decreasing speed. So left, well, let's see, that's below. Okay, so, well, that does say below. God help us all. Okay, so that is below with decreasing speed. So that means if my speed is decreasing and I'm below, then my function itself has to be increasing. Well, let's look back at the graph and see. Is my function increasing between B and C and below? Well, it is, so the particle's moving left with decreasing speed because my speed should be decreasing there because velocity is negative, but the graph is increasing. So the correct answer here would be B, strangely enough. All right, let's see what some of the other answer choices would be just in case. Make sure we didn't miss it. So C, the particle is moving to the left with increasing speed. That would be speed increasing. We would have to be below and decreasing because here if my particle is moving left, I know I'm below, but my speed is not increasing because my function, while it is below the x-axis, that function is not decreasing, so speed cannot be increasing. That's confusing. Okay, part D, the particle is moving to the right. Well, we can stop there. That's completely wrong, crackhead. And then let's see, and E, the particle is moving to the right. So again, we can throw those out. All right, so now let's go on and look at number 12, or I'm sorry, 13. Now I'm a crackhead. Number 13. Let's see, 13, using the information shown in the graph, at what time t does the particle reverse direction? So in other words, what time does the particle change directions? And I think that's safe to say particle is changing from left to right here. So yeah, that's going to be answer choice C. All right, so let's give a couple of these free response problems a look at. And this is a really good traditional problem that you see quite a bit on the AP exam. And you're always going to have, it's usually a person riding a bicycle, driving a car. There was a squirrel at one time, believe it or not. But they all are basically the same thing. Notice that you're given the graph of velocity. So that's something that you always need to know. You've got velocity. And you have an initial position here at time 0 minutes. And arriving at school here at time 12 minutes. And then you've got, let's see, you've got your units. So we do need to pay attention to miles per minute. All right, and then here, this is always important, but we're so tempted to skip over it. We have a piecewise linear function. Now, the reason why if we know that we have a linear function, then we know we have changing y's over changing x's. And we also know that we can come up with y minus y1. We have this equation of a line that we can come up with. So those things we're guaranteed if we're told we have a linear function. So those are some things that we need to get in our minds when we see linear function. We need to be thinking this. Okay, so for the first part here, we're told that we need to find Karen's acceleration at 7.5 minutes and indicate our units of measure. Now, at 7.5 minutes, we have to be careful here. We're looking at velocity, but they're wanting us to somehow approximate acceleration. So at 7.5 minutes, where is that going to be? Well, here's at 7 minutes. Here's at 8 minutes. So somewhere in between here. And please don't approximate that. You can find that exact value, and that's what they want you to do. This is a 2-point question, so please make sure you get this. Every point matters. So our acceleration, so I'm going to start out, and notation is so important here. So we're going to start out our notation with A, because that's our acceleration, at 7.5 is approximately, because we are approximating this. We're doing A rock to find I rock. And between what two values would I find here 7.5? Well, we would have V at 8 minus V at 7 all over 8 minus 7. And then that is equal to 0.2. Go look at your graph. That's where I'm getting these numbers. Minus 0.3 all over 1. And so here I get negative 0.1. And we don't need to forget our units. And keep in mind it's going to be, look, we were given miles per minute. So we have miles per minute. But then it's also, again, per minute. Miles per minute, that was the units of my numerator, and then my denominator is also per minute. You're more than welcome to write per minute squared if you wish. Either one is acceptable. Okay, so let's look at part C. And we've edited out part B just because there's no way for us to do it right now with what we know. And so shortly after leaving home, Karen realizes she left her calculus homework at home. And what a great student. Look at what she does. She turns around and goes and gets it. That is crazy. At what time does she turn around and go back home to get her calculus homework? And give a reason for your answer. Okay, these problems always get students because looking at the graph, you're going to realize the velocity goes from a positive to a negative, and you're going to say that at time t equals 2, and that's going to be all you do on this problem, and you're going to lose some of your points. So that's why I want y'all to be super careful here. Yes, at time equals 2, Karen does turn around, and we can go ahead and write that at t equals 2. We know that Karen, I think that's how you would pronounce that, turns around. Now, you need to state why you know that. Now, don't go off on some crazy tangent here. Just state why you know Karen turns around. Well, we know she turns around at time t equals 2 because, and notice that she has her velocity changing because v at t goes from being a positive value to a negative value. At that time, and that's really going to be all you need to put there. So again, be careful with what you write. Use your problem to answer this. Get your words from the question itself. Let's see, at this time, and that's really all you need to put here. That is it. So be careful with these. That one was also 2 points. You got a point for your time and then a point for your justification. Okay, so here's another great free response problem, and we can already do some of it. Now this one we have to be really careful because our graph has changed. Our graph now is no longer of velocity. Our graph this time is talking about acceleration. So we have the second derivative graph. Do keep that in mind. And so here they are asking, is the velocity of the car increasing at time t equals 2? Why or why not? So please, for the love, don't just write yes or no. You need to state why you know what it's doing. So let's see, at time, so let's start this, at time t equals, and for the love, don't miss that, time t equals 2, the velocity of the car, and now we need to make a decision. So the velocity of the car is doing what? So at time t equals 2, what is the velocity of the car doing? Well, let's go look at time t equals 2. Well, at time 2, we see that acceleration up here, our acceleration is positive, isn't it? Here at 2, we are above, so I know from here to here, a at t is positive. Well, if a at t is positive, that's going to be the derivative of velocity. So if my derivative function is positive, then I know my original function was increasing. So at time t equals 2, the velocity of the car is increasing. And again, why do I know it's increasing? It's because, and this is your justification, this is your why or why not, a at t is positive. That's how you know what is going on here. Okay. So for 16, we have part B. A car is traveling on a straight road. The car's velocity, so again, we have velocity given to us in meters per second. So we have our units. Is modeled by, yay, again, we have a linear piecewise function. So for part B, we have to state for each of v prime at 4 and v prime at 20, find the value or explain why it does not exist. Indicate a unit of measure. So let's see, v prime at 4. Well, let's go look and see. V prime at 4. So right there, notice what's going on graphically with this. We have a sharp point here. So at v prime at 4, it looks like if we have a sharp point, then we know we are not differentiable there. So v prime at 4 will not exist. Okay, so here, that's not going to exist because, and let's see, why would we say because v of t is not differentiable? At t equals 4. Okay, we have that sharp point there, so we're not going to have a value. Now, don't be tricked by this problem. And I say that because if we look up here, and I'm going to do v prime at 20 up at the top. Now, look at for v prime at 20. A lot of kids, when this problem was given on the AP exam, a lot of students looked at that to be v prime at 20 and wanted to say the same thing about v prime at 4 for v prime at 20. But this is not v prime at 20. Remember, 20 is a time. So really v prime at 20 is right in here. we can find that the v prime at 20 is going to be the slope of your tangent line here. So really, all we have to do to find v prime at 20 is going to be equal to, well, it's just the slope of this line segment from here to here. And notice that what 2 points we have. We have points 16, 20, and we also have the point, I would use this one down here, 24, 0. So now all we have to do is our changing y's over our changing x's. So we have v at 24 minus v at 16 all over 24 minus 16. And so v prime at 20, that's going to be equal to, and let's see, v at 24, we chose that because it's 0, minus 20. And what's 24 minus 16? I think most days that's 8. And let's see, so that's going to give me negative 20 over 8. And we can leave it just like that. Now let's indicate our units of measure. Let's grab that last point. So our units of measure is going to be meters per second. And again, we second over per second. So let's go ahead and just say meters per second squared. All right, so for part C, very similar, same graph here, but now I'm talking about A at t, and they want us to write a linear, is it linear? No, it's just a piecewise defined function for A at t. This problem had a very low scoring percentage because a lot of students were like, well, I don't know what to do with acceleration. I've got the velocity, or they tried to write some equation for this graph up here. Now, again, keep in mind how these are related. If we do the derivative of velocity, that's where our acceleration comes from. And again, all the way back to the very beginning of this course, if we talked about a derivative, that was also the same thing as talking about slope. So if we put that into perspective, then we will realize that all we're doing is writing a piecewise function describing the slope of these lines. That's all this is talking about. And we really have 3 different line segments here. We have from here to here is a segment, we have from here to here is a segment, and then from here down to here is a segment. So we have 3 different segments that we're going to write the slope of these lines for. And that's really all we need for this problem. So I'm going to say A at t equals, and we have a piecewise, so we're going to have to divide this up into 3 different parts. And now for the first part, let's see if we can't find a slope for that particular interval. So again, I'm looking over the interval from 0 to 4, and that's going to contain this line segment here. So we could already say, well, I'm talking about from 0 is less than, and it really doesn't matter here as far less than or equal to. I just do less than. Okay, so for my time between 0 and 4, what is the acceleration or the slope of this? Well, if we're starting at 0, 0, aren't we? So our rise, we rose 20, we went over 4, so really that slope is going to be 20 over 4, or you could even write 5, and that's all you need for that, because that is the slope there. It's going to be just 5. Okay, so let's look at our next interval. Well, our next interval would be from here to here, which is going to be from 4 out to 16. So from 4 to 16, let's see. Well, what's going to be the slope of that? Well, this is a horizontal line, isn't it? Slope of horizontal line is 0. Well, okay, that's not too terrible. And then let's look at our last one, our last segment. And if we remember what we just did in our part B, we already have that value, don't we? We already found that. So from 16 to 20, so from 16 to 20, if we remember what our previous answer is, we already have that acceleration because we calculated it. That was negative 5/2. And voila, we have our piecewise defined function for our acceleration. Very good problem, a very doable problem. It does test whether or not we understand how velocity and acceleration are related and the whole idea of a derivative. Okay, moving on to the next question. Find the average rate of change of V over the interval from 8 to 20. Does the mean value theorem guarantee a C for the interval 8 to 20 so that V prime at C equals this average rate of change? So, wow, that's a freaking lot of stuff here. All right, let's see if we can break it apart. So the first one, find the average rate of change over the interval from 8 to 20. Okay, so we can jump on that one. Average rate of change, A rock. All right. So average rate of change over that interval, well, we would say V at 20 minus V at 8 all over 20 minus 8. And that's going to be equal to negative, I'm going to go ahead and reduce it, but you don't have to, negative 5/6. And we have meters per second. Average rate of change, so meters per second. So now it wants to know here, do I have a value such that, well, let's look at what it's really asking here. So we're looking for a C that is inside this interval from 8 to 20. So 8 to 20. So I'm going from 8 all the way out to 20. So here to here. So that's going to be about from here to here. So right through there's 20. So it's talking about this portion right here. So it wants to know, are we guaranteed a C so that V prime at C equals this particular rate of change? Well, let's look at what's happening over that interval. Notice that right through here, we really have a sharp turn there, don't we? If we go back and we focus on from 8 to 20, look at what happens over that interval. We're not differentiable there. So will the mean value theorem guarantee? Well, mean value theorem says that we are differentiable on the closed interval. We're continuous on that open, or I just said that backwards. We are differentiable on the open and continuous on the closed. So no, it doesn't. So my answer here would be no, because V at T is not differentiable, and I'm getting lazy, so I'm going to put DIFF at, and where do I have that sharp point at T equals 16? So no, I'm not going to have a derivative there. So if we're not differentiable over that open interval, then we cannot say that that's guaranteed.